Welcome to the third installment of my video series, in which I aim to shed some light on some of the most impactful supervised learning models for parameter estimation in specifically the physical layer of wireless communication systems. All of my videos in this series take insight from Mcclintick et al.'s published work that I have linked in the description below. This is truly a great resource if you are interested in learning more about this application. Before I jump in, today's topic does relate to both my video on convolutional neural networks and K's nearest neighbor, so I suggest you give those videos a watch before diving into this topic. Previously, we have explored the convolutional neural network and K nearest neighbor models. However, the topic of discussion for this video is the support vector machine. I would like to begin our discussion by first explaining some of the fundamental concepts behind the support vector machine model. Then we're going to spend some time exploring one of the most integral parts of this model, the hyperplane. Following this, I will then go into a bit about how classification of input data is accomplished using this model, and even how we can maximize model performance for our classification problems. We may recall that K nearest neighbor, using a training data set, works by calculating the proximity of the query point to other points of a given class. The support vector machine adds a bit of dimensionality to this approach. Similar to the K nearest neighbor model, the classification of a data point is dependent on its proximity to training data points of a given class. However, from a mathematical perspective, the support vector machine model forms these class divisions not through the grouping of data points, but through partitioning them. Now, I understand these might sound similar, but let me illustrate the difference. Instead of trying to identify which data points are close to each other, the support vector machine model attempts to draw boundaries between groups of points or classes by identifying which data points are the furthest apart. One of the concepts at the foundation of the state vector machine model is the hyperplane. The general definition of a hyperplane is any codimension 1 vector subspace of a vector space. We can see here that C refers to a subspace of the vector space R in which X is defined. In other words, C is a hyperplane of the vector space R. Now, there is a lot of complicated and confusing terminology in this general definition, so let's explore this more theoretically. Imagine we have an input data set that has, let's say, 2 unique features. A feature, in this case, being a defining characteristic of that input data. Now, what if we want to classify this input data set based on these features? We are going to need to be able to separate the input data into separate groups or classes. Now, like in the case of the K nearest neighbor algorithm, we could just draw a single dimension line serving as a decision boundary between each group. But what if this input data is multidimensional? What if there are many input data features instead of just 2? Well, we could instead draw planes, like can be seen here, to separate the data given that it has more than one dimension. But this still doesn't solve the issue of needing to create multiple classes given multiple input features. This is where the hyperplane comes into play. The hyperplane can be visualized as a series of planes that all intersect at an origin point. The dimension of the hyperplane, or the number of individual planes that comprise the hyperplane, is one less than the number of input features in the dataset. So an input dataset with 5 features would require a hyperplane of 4 dimensions. So now going back to that general definition, we can think of the space in which the input data exists to be the vector space, and the space that is occupied by input data of a given class or a set of features to be a vector subspace. Each of these subspaces within the vector space share a single dimension, indicating that an origin within the vector space exists where all of these subspaces intersect. In the concept of physical layer parameter estimation, it is possible to have either single or multiple dimensions of data. So now that we've kind of established what a hyperplane is and how it can be used to classify data, you might be wondering, where exactly should subspace boundaries be drawn to achieve the best classification results? So let's imagine that we have a set of training data points and we want to divide them into 2 distinct classes. How would we go about choosing where the hyperplane should go? Well, as a general rule, the location of each segment of the hyperplane should always maximize the margin between the 2 classes. When this is satisfied, it helps ensure the greater level of confidence in future classification solutions. So what do I mean by maximizing the margin? I mean we should select the boundary location so that the distance between the data points closest to the decision boundary is the largest that it can be. We call this location the optimal hyperplane. The higher dimensionality of the input data set, the more complex determining this optimal hyperplane is. But not to fear, there are tools available to help. One tool that is commonly used to ensure the optimal hyperplane is achieved is the support vector. Support vectors are defined from the points that are closest to the separation point between the 2 classes. We can define a large number of support vectors between these classes, as can be seen by all of these gray lines on the left. However, the objective is to find a set of support vectors that are separated by the greatest distance. For example, in this case, the best support vectors between the red class and the orange class might look something like these in green, where the vectors are parallel to each other and the distance between them is the maximum that it can be. The optimal hyperplane location can then be identified as the boundary that is equidistant from both of these support vectors. Now that we've developed an understanding of this theoretically, let's examine some of the math behind it. We have already established that the support vector machine model aims to maximize the separation between points of different classes. In addition to the use of support vectors, calculating hinge loss can also help us to achieve this maximum separation. Hinge loss is a loss function used primarily for support vector machines. These rely on finding the maximum margin between input data in order to draw these class boundaries. This here is the hinge loss function, where t can be equal to either positive or negative 1, and y is the output of the classifier, which is also either positive or negative in sign. To elaborate a little bit further, y is dependent on the parameters of the hyperplane, w and b, in the input variable, x. If the sign of t matches the sign of y, let's say that both are negative, then we know that the proper classification of a given input data point was made. However, if the signs of t and y are not the same, then the data was misclassified. Misclassification indicates that the support vectors chosen to define the hyperplane did not result in the optimal hyperplane. An iterative approach is often employed to select support vectors, define the hyperplane, and calculate the hinge loss as an indication of classifier performance. If misclassification does occur, different support vectors are chosen and the process begins again. Thank you guys so much for watching. Although this is the last supervised learning algorithm I will discuss as a part of this video series, I hope it has been instructive. If you want to learn more about the support vector machine model, specifically for parameter estimation in the physical layer of wireless communication systems, I highly suggest you take a look at the references I have linked below.